Arthroscopic debridement is a surgical intervention for articular degradation where damaged articular surfaces are shaved down to minimize inflammation and pain. Current shavers utilize a rotating drum-shaped shaving head that, when pressed against cartilage or bone, can cause ripples, which creates a suboptimal post-surgical result. Our team is driven to optimize arthroscopic debridement by creating an arthroscopic shaver that creates smoother articular surfaces, which results in a post-surgical joint that provides an improved quality of life for patients.
This project is important both on the small and on the large scale, and our project is meant to ultimately improve the efficacy of arthroscopic operations overall and improve short and long-term joint function for the hundreds of thousands of individuals that undergo arthroscopic debridement every year. This procedure is a great alternative to total joint replacement.
When beginning our design, we tossed around a couple different ideas for the shaving smoothing mechanism. We ultimately decided on a drive shaft with a fixed rectangular head with curved edges to be able to travel smoothly over rough surfaces while also operating with a side-to-side vibrating motion. Through this process, I created a 3D model of our design in SolidWorks. Included in this final assembly are the drive shaft, the outer shaft, the fluid chamber, the motor, the circuit board with an on and off trigger control, a charging port, and a battery compartment.
We were lucky that our university has a shop that has the needed machines, which made our project easy to build. We used the shop to cut the inner and the outer shaft using the bandsaw machine and make a head and drill it with the lathe machine to attach it to the inner shaft to meet the specifications of the design.
In this case, the main power component is the vibrating motor. For vibrating motor, we needed a circuit board to switch the voltage between the positive and the negative at a certain frequency.
On the circuit board, we used a programmable microcontroller. In the whole circuit, we will connect the recharge battery to force the whole circuit.
Throughout our project, we have gained valuable practical experience following the engineering design process. We have learned the importance of collaboration, communication, and the impact of technological advancement through engineering. While many current surgical technologies are already very advanced, it can always be improved to ease surgeons' lives and improve patient care and successes.
I am pleased to see an excellent prototype design from this interdisciplinary team using state-of-the-art electromechanical components.